Hi everyone, I'm Chen. Welcome to the COMET workshop, which is I think it's very useful workshop. I was benefited a lot when I was a student at UK, and it's good for InSAR beginners. I think really helpful. Today I'm going to talk about after team. Today I'm going to talk about the some errors occurred on our InSAR measurements. I think many of the audience have already concerned about this problem, and they ask us about how can we mitigate errors on InSAR measurements. First of all, let me introduce myself first. Sorry, I'm Chen from Chang'an University in China, and I was a former PhD student at Newcastle University, which is part of COMET, and I'm now researching on natural hazards, including earthquakes, volcanoes, landslides, and extra using geodetic observations, mainly InSAR and some GPS and UAV data. So that's my research. Today, my topic is about InSAR atmospheric effects and its mitigation measures. So the objectives, sorry, the objectives of this lecture is to introduce what are atmospheric delays. So what's the definition of atmospheric delay, and what it looks like on our InSAR measurement. So many observations will have this kind of error. So what it looks like on InSAR, and finally the most important thing is to how to mitigate this kind of error on our measurement, so that we can get a clean deformation map. So this is the objectives of this lecture. So what is the atmospheric delay? What is the atmospheric delay? So we all, I think Tim has already introduced this, the basic principles of InSAR. How InSAR works is like this. The satellite of InSAR flies above the Earth. So it transmits a signal, a microwave signal from the satellite to the ground, and it got reflected by the ground, by a target on the ground, and received by the satellite. So it measures the traveling time of that signal. And then because we know the traveling speed of the signal, which is the speed of light, a kind of a constant, so we can calculate the distance between the satellite and the ground target. So this is the ideal case. So this is the equation we use to calculate the distance. This is our measurement. But however, because of the existence of the troposphere and the ionosphere above the Earth, we all know that the atmosphere actually, the signal got affected by the existence of the atmosphere. For example, in this figure, because the air, the density of the air becomes larger, is larger near the ground and the smaller about high in the sky. So the signal, the traveling path of the signal will be affected, will be curved by the atmosphere. So the real path of the traveling signal, this is only an imaginary path. It's a false path, not a real path. The real path looks like this. The real path looks like a red line. So it's curved. It's not a straight line. So it's curved. The curvature of this path depends on the troposphere and the ionosphere. So it's dependent on the location of the signal. So this equation doesn't work for this real path. So we have to use this equation. This is the correct equation. So the traveling speed of the signal is changing place by place. So the speed of the light is affected by the atmosphere. And also the path is not a straight line. So we have to use this integration equation instead of directly multiply it by time. So this is the real equation we have to use to calculate the distance. However, it is very hard to measure the speed of light, to measure the real path. So we have to use this simple equation. And instead of using the real equation, we add two error terms on this simple equation. So one is called the ionospheric delay. One is called the tropospheric delay. So there are two error terms. One is caused by the ionosphere. One is caused by the troposphere. So the ionospheric delay is also very large compared to the tropospheric delay. So it is inversely proportional to the square of the frequency. So it depends on the frequency of the signal. Our lecture today focuses more on the tropospheric delay, which is frequency independent. So no matter you are using ILOS data or you are using Sentinel data, the atmospheric delay is actually the same. It's independent of the frequency. Some literature may call the tropospheric delay as atmospheric delay. It's actually the same in InSAR community, not in other communities. So we call atmospheric delay equivalent to the tropospheric delay. So you have to notice that for the ionospheric delay, which is also an important error on InSAR measurement. And there are many ways to mitigate ionospheric delays as well. For example, the split band technique, which is very important, especially when you consider the launch of NISA next year, because NISA has two antennas, so it's easier to do the split band technique, I think. So which is more important new in InSAR communities. You can have a look at this new InSAR satellite. So which is ideally designed for mitigating ionospheric delay. So our lecture today is focusing on the tropospheric delay. So this is the basic structure of the troposphere. So it contains 80% of the air mass and 99% of water vapor. Because the delay, the tropospheric delay, is mainly caused by air pressure, temperature, and most importantly by water vapor. So that's why tropospheric delay happens mainly in the troposphere. So the absolute value of the tropospheric delay can reach 1 to 3 meters. So it's really large along the zenith direction. Along the line of sight direction, it can reach probably 4 to 5 meters. So it's really large. Traditionally, the tropospheric delay can be divided into a hydrostatic component, which is relatively stable in space and in time. So very easy to predict. And also a wet delay, which is variable, highly variable, and very hard to predict, very hard to observe, very hard to estimate. So this is the wet delay is the most important component in tropospheric delay. The tropospheric delay is a very common error source in many observations, including, for example, GNSS and InSAR, of course, and also, for example, satellite altimetry and very long baseline interferometry. So all these kind of measurements are contaminated by the tropospheric error. So it's a very common error source for most Earth observations. So there is a lot of research is talking about this kind of error. So we have talk about the definition of tropospheric error and what caused the tropospheric error. So what it looks like on InSAR, how it is acting is what's the effect of the tropospheric error on InSAR measurement. Before that, we have to know that InSAR measurement is different in time. So that we always have we have a reference date. For example, for any interferograms, we have a second date and the first date. The measurement is different between the second pass and the first pass. So it's temporally different. So it's a different measurement, not absolute values. Apart from that, InSAR measurements are also different in space. For example, we will always have a reference point on our interferogram. So all the measurements are referenced to that point. So we cannot measure absolute deformation. We can only measure relative deformation. So deformation relative to a point, to some places. So this is InSAR measure. So if we change the reference point to another location, you will result in this interferogram. Actually, these are two same interferograms, just with different reference points. So to conclude that InSAR measurement are spatial temporally difference is a double difference measurement. So what we will concern in InSAR is not the absolute value of the tropospheric delay. It's a double difference tropospheric delay. So what we are concerning is the spatial temporal changes of the tropospheric delay. So how can the tropospheric delay change in time and in space? So this is a figure video showing how the water vapor is changing through time globally. So we can visually see the changes of the water vapor from space to space. So this is a global scale. So you can still see the changes very rapidly. This is in 1 day, only in 1 day. This is hourly temporal resolution. You can see it changes very quickly. So which means the changes, this kind of changes can cause very serious tropospheric error on InSAR measurement, because what we are concerning is the changes of the tropospheric error, not the absolute value. And also this is an example showing the changes during of the water vapor during a storm in the UK. The storm happens in 6 p.m. Around 6 p.m. you can see there is a great jump in the errors, in the tropospheric error because of the storm. So it can cause very large changes, above 10 centimeters sometimes. So it's quite large during the storm. So this kind of change, if the troposphere is not changing through time, over time, we can estimate it very well. But if there is a storm, there is a rainfall, there is a sudden changes in the troposphere environment, the error will be very large. So the changes is very important. So to summarize that it is the spatial temporal variations in the temperature, pressure, and water vapor that result in the atmospheric effect on InSAR measurement. And the variation of water vapor can be large and can be rapid. And the absolute value is about 2 meters along the zenith direction. But after double differencing, after spatial temporal differencing, it can reach 5 to 20 centimeters. It's still quite large compared to many deformation signals. So this is the basics of the atmospheric delay. Okay, so that's the theory of the atmospheric effect on InSAR. So what it looks like, how can we visualize the effect on InSAR interferograms? I will give you some very standard, popular used examples showing the tropospheric error on InSAR interferograms. These are several interferograms in the UK, in the south of England, from Sentinel-1, 12-day interval. You can clearly see the blue signal, the blue color. These are all tropospheric error, actually, because there is no deformation happened here. So all you can see is the tropospheric error. It's called the long wavelength effect because it's directional. So there is a direction in the signal. So for example, from south to north, from east to west. So it's directional. It's kind of a trend effect. And if you zoom in a smaller region, it may be constant. But if you zoom out to a larger region, you can clearly see the effect. So it's long wavelength effect. If only apparent on large interferograms. So if you zoom in smaller interferograms, you may probably see you may you cannot see this signal on smaller interferograms. So it's only apparent on large interferograms. So this is called the long wavelength effect. So how to understand the long wavelength signal? It comes from the Fourier transformation. So for short wavelengths, it typically means noise or random noise. And for longer wavelengths, it typically means a trend effect or nearly constant over small areas. So for short wavelength signals, we have, for example, the landslide or mining cost subsidence. These kind of signals are relatively in short wavelengths. But for coseismic interferograms or volcanic eruption caused deformation, which is relatively between short wavelengths to medium wavelength signals. But for post-seismic or interseismic, for this kind of deformation phenomena, it typically has very long wavelength deformation signals. So different deforming scenarios we may have different wavelengths of signals. So if you are studying plate motions, large-scale plate motions, or rotations of a plate, you may probably encounter very serious long wavelength affection caused by the troposphere. So because tropospheric effects have a very large long wavelength component, which is quite similar to your deformation signal. So it's very, very hard to consider that. But if you are studying landslides or you are studying coseismic signals, probably this kind of long wavelength errors is not that serious. It's independent with your deformation signal. So it's easier to look at landslide signals from the long wavelength errors. So it really depends on which kind of deforming scenario you are studying. So this is the long wavelength effect. Apart from so the long wavelength is not only the atmospheric delay, there are many other error sources that can cause this long wavelength effect, including for example the ionospheric delays. It's quite similar to the tropospheric delay, and the ocean tide loading errors, orbital errors, solid Earth tides. There are a lot of error sources that can cause this long wavelength effect. And sometimes, for example, in the UK, the ocean tide loading effect can be equivalent to the tropospheric error. So in magnitude, they are actually about 1 to 2 centimeters in time series. So there are a lot of different kinds of long wavelength errors. Tropospheric delay is only one of them. And because of this long wavelength effect, so the noise level in our time series, in our deformation time series, is distance dependent. So it really depends on the size of the interferogram. So the longer the baseline, the larger the noise level. If you are measuring, for example, if you are measuring a short baseline, you are measuring this short 2 kilometer separation, the relative deformation between these 2 points separated by 20 kilometers, for example, you have a very low noise level. So the tropospheric error is relatively small in this case. But if you are measuring long baseline deformation between, for example, separated by over 100 kilometers, you will encounter much larger noise level because of the troposphere. So the size of the interferogram really matters. If you are processing very large interferograms, it will be very hard because of the tropospheric error. But it's much easier. It will be much easier to process smaller interferograms. This is the long wavelength effect, actually. Another very important effect is called the elevation dependent effect, which you can see from these two figures. It's maybe irrelevant to the size of the interferograms. So you can see it clearly on large interferograms, or in this case, and you can also see it on a smaller interferogram. So even for this 8 kilometer interferogram, it's a really small interferogram. You can clearly see the the tropospheric effect because of the variations in the topography. You can clearly see it's similar to a DM. Because the absolute atmospheric delay are negatively correlated with the elevation. So it's negative correlation. But after double differencing, after spatial temporal differencing, this correlation can be either positive or negative. So it's really depends on the location, on the time of the interferogram. So it's variable. Even on the same image, for example, for this same image, different locations may have very different correlations between the phase and the elevation because of the troposphere. So for example, the left of the figure, you have a very nice linear correlation between the phase and the elevation, which is caused by the troposphere. And then in the middle, you got some kind of nonlinear correlation. And in the right-hand side, you got very large nonlinear component caused by the troposphere. So even on the same image, you have very different correlations caused by the troposphere. So this is called the elevation dependent effect. And they are also very hard to predict, very irregular noise caused by the troposphere. For example, this wave effect, probably you may see it in coastal areas. This is the from in New Zealand, and this one is in the UK, in the Western England. So you can clearly see the wavelength, the wave effect, which is really random. And we don't know why this happens, but it's really annoying. It's caused by the troposphere. Very hard to predict. And also there are some turbulent, kind of random effect on some interferograms. You can see it's not it's really irregular and hard to predict. You cannot use one equation or to model this kind of effect. So it's hard to model because it's turbulent and very unpredictable. This kind of errors is called turbulent effect. So all these are tropospheric effects. Okay, probably it's a little bit complicated, but all these effects are called tropospheric error. And so I think most of us are using Sentinel, especially in this workshop. There are some practicals using Sentinel data. So what's the tropospheric error on Sentinel observations? This is a map showing the magnitude of the atmospheric effect on Sentinel-1 descending tracks based on real Sentinel-1 satellite geometries. As you can see, this is for descending tracks. We have nice coverage globally. In north of Australia, south of the USA, southeast of USA, and in India, east of China. So these places cannot have much larger tropospheric effect than other areas. So this is a real magnitude of the atmospheric effect on Sentinel-1. This is for Sentinel-1 ascending tracks. We have a poor coverage by ascending tracks. So as you can see, the tropical area, actually the tropical areas always have larger tropospheric effect than other areas. So this is probably you can refer to this map to check if you have very serious tropospheric effects on your interferogram, depending on the location of your interferograms. And to summary, there are a lot of different kind of features of the tropospheric effect or atmospheric effect on an interferogram. It may include long wavelengths, elevation-dependent signals, distance-dependent signals, wave effects, and turbulent signals, random delays. So all these components are mixed together, probably on an interferogram. So you have to really careful when you look at the interferogram. You have to consider whether it is dominated by long wavelengths or dominated by elevation dependent or both. So you have to really careful with that. So we talk about the definition, how it looks like on InSAR measurement. So why do we do we concern about this kind of error? So can we just ignore it? So why do we do this atmospheric correction? So there are a lot of benefits actually. Here are some examples. The first one is the post-seismic velocity mapping. If you are to post-seismic study, if you ignore the tropospheric error, you will result in this velocity map. Without atmospheric correction, you can see this clearly long wavelength errors still exist on your velocity map. But after correction, you got much cleaner velocity map, which you can clearly see the deforming signals. And this is the model. You can clearly see you have much smaller residuals after correction. So if you do not consider deal with the atmospheric error carefully, you got very noisy time series results, and you got very biased velocity mapping. So that's the one benefit. Another benefit is that if you look at the volcanic deformation signals, you can clearly see the tropospheric error is quite similar to the volcanic deformation. So if you look at the original interferogram, you will probably think that there is something happening around the volcano, but actually it's not a real deformation. It's caused by the troposphere. There is nothing happening around the volcano actually. So if you do a time series analysis, you want to check whether there is some early warning signals. There are some deformation signals before the eruption of a volcano. Actually, you can see nothing from the original time series. For example, the point B is outside the volcano. Outside the volcano, point A is on top of the volcano. You can clearly see there is no differences between these two points, even before the eruption. But after tropospheric correction, you can clearly see the point on the volcano has a clear jump, clear deformation signal before the eruption. So you can use this kind of signal to warn people around the volcano, to do early warning tasks based on this kind of observation. So it's really important in early warnings. So we can clearly see these warning signals after atmospheric correction. So it's really important to do the correction. Also, we can clearly see we can also benefit from detecting smaller landslides. For example, if you do not correct for the tropospheric error, you can see the landslides are covered, are contaminated by the tropospheric error. All you can see is the red signals. You can hardly identify landslides in this figure. But after correction, you can clearly see those landslide signals stands out. You can clearly you can identify locate those landslides much more easily after correction. So there's another benefit of doing atmospheric correction. So this is the background of the definition of the atmospheric effect, how it looks like on InSAR measurement, what's the features of the tropospheric effect, and why do we do the atmospheric correction, and what's the benefit of doing so. So the most important part is to introduce how do we do the correction. There are many different kinds of methods, different strategies, different algorithms to do the correction. I divided all these kind of methods into 3 different types. The first strategy is to use empirical models. To use an empirical model. Actually, this kind of strategy is to play with the interferograms themselves without using any external datasets. If you only have one interferogram or a time series of interferograms, you don't have to download additional datasets such as weather models or GPS or any other things. You you can only use your own interferograms to do the correction. This is the benefits of using this kind of strategy. The basic steps of this strategy is to, firstly, you have to assume an empirical equation. So you can use this equation to model the tropospheric error, and then estimate the parameters in this equation based on your own interferograms only. And then you can produce a nice correction map to do the correction. I will show you some popular examples. For example, in this case, if you have linear, so you can have this linear equation. So you can assume that all the tropospheric delay, all the atmospheric delays are correlated with the elevation, which, because we already know that it is correlated with the elevation, and it has a elevation dependent component. So we can assume this equation. So the atmospheric delays are correlated with elevation linearly. So then you can use your own interferograms to estimate A and B, parameter A and B. And then after that estimation, you can produce a correction map like this. This is the correction map based on this equation. And then after correction, you got this corrected interferograms. Compared to the original interferograms, you can see the performance. Basically, it assumes that all the signals on your original interferograms comes from the atmospheric delay. So all the phase measurements are actually tropospheric delays. So you can use that tropospheric delays to estimate A and B, because you already know the elevation of each point. So after that estimation, so you can calculate the residuals of this equation. The residuals actually means the corrected interferograms. So this is the basic steps of this method using the linear correlation method. And also you can assume this kind of equation. This is a ramp equation. This equation deals with the long wavelength effect much better. So if your interferogram has this kind of long wavelength effect, so you can see it's not correlated much with the elevation, but it has a very clear trend directional signal from east to west. So it's called the long wavelength effect. So you can use this equation based on the locations of each pixel, and you can estimate 3 parameters in this equation. Or you can use more complicated equations, but it's typically the same. And after estimating A, B, and C, you can produce a nice correction map. And this is the performance of this kind of method. Remove ramps from the interferograms. This is another type of method. But if you have long wavelength deformation signals, you may probably remove them as well. So you removed all the long wavelength signals, no matter it is tropospheric delay or no matter it is caused by actual deformation. So you cannot distinguish between these two. You removed all of them. So this is the risk of using this kind of method. And another method is to use this equation. So this equation the power law equation deals with the turbulent or random tropospheric delay. If your interferogram looks very noisy, and there are many random noises on your interferogram, you can try this equation. This deals with the short wavelength random turbulent tropospheric delays. You can use the equation and estimate parameters alpha here, and then produce a correction map. This is the performance. And also in this equation, you can also consider the height, the elevation of the interferogram. You can add more parameters into that equation and to do the correction. So it's basically the same, just using different equations to estimate the tropospheric delay, depending on the dominant tropospheric error, whether it is long wavelength signal or whether it is elevation dependent signal. So it depends. But what about if we don't know the the tropospheric error, which component is dominating on our interferogram. Sometimes we don't know which component, such as long wavelength or elevation dependent or turbulent signal. We don't know which component is dominating on our interferogram. So we can try this method. So the principle, the component analysis or independent component analysis method. But actually, this method can divide the original interferogram into different components. So probably the first or the second component maybe comes from the troposphere. So you can remove that component and then do the correction. So this is another method in cases that you don't know which component is dominating on your interferogram. So this probably performs better in that case. Or we can try deep learning. So it's much easier to understand that you don't have to care about which component is dominating on your interferograms. You don't care about that, and you put all the interferogram into the training, and then you train the data set and then do the correction. So the network will learn which component comes from troposphere, which component comes from deformation. So they split these two, and to result in a corrected deformation map. The algorithm is really complicated, but the basic idea is simple. Just to divide your interferogram into different components. One component comes from deformation, and other components come from noise. So this is the basic idea of this method. This is another method based on deep learning. So you can clearly see it can recover the co-seismic signal very well, which are covered by tropospheric errors or other error sources probably before correction. So this is deep learning, which is very popular in these days. And to conclude, the advantage of this method is that it's very simple to implement because we don't rely on external data sets. All we need is just an equation, and you can play with that equation with your own interferograms. So it's very easy to implement, but there are many disadvantages. First of all, it risk of removing extra deformation signal. So for example, if your deformation signal is correlated with height, so such as the volcanic deformation signal, which is correlated with height, with the elevation as well. So in this case, you will remove the actual deformation signal if you use the linear correlation method. So the risk of removing actual deformation signal, and also the estimation of the equation. So all these equations can be disturbed by other error sources. If we all know that there are many different types of error sources in our interferograms. So if there are very large ionospheric delay, or there are very large ocean tide loading signals, this kind of errors will bias our estimation in this type of method. So, and also sometimes it rely on manual interactions, especially when your interferograms becomes very large. You are processing very large interferograms. Sometimes you have to divide a large interferogram into smaller ones, into smaller patches. So in this case, you will rely on manual interactions to produce a nice correction map. So these are some disadvantages. Okay, that's the first strategy. The second strategy is the external datasets. Apart from using empirical equations, we can use external datasets. For example, we can use ground-based, satellite-based, or integrated observations, which is called a numerical weather model, which contains both ground-based or satellite-based data. So there are a lot of data actually we can use to correct for the tropospheric error. The first one is comes from the satellite-based space-based water vapor sensors. It has a global coverage, around 1 kilometer spatial resolution, and a 1-day temporal resolution. This is a map showing the MODIS satellite, I guess. And this is the water. This satellite directly measure the water vapor content in the troposphere, so it can directly produce water vapor maps or correction maps for our InSAR atmospheric correction. This is an example. The water vapor map from the first date and the second date, and then the difference map, which is the correction map for InSAR atmospheric correction. And this is an example using this kind of observation. The left one is our original interprogram, and the right-hand side is after water vapor correction, after correction. But you can clearly see this long wavelength effect, which is caused by the orbital error. So after removing that orbital error, you got very clean cosmic interprogram. So this is the performance of using the MERIT, which is pretty good. But the drawbacks of using this kind of equation is that it ignores the hydrostatic delay. The dry component is missing because it only measures the water vapor, not the pressure, not any other parameters in the troposphere. So it can only give you the wet delays. The dry delays, the hydrostatic delays is missing from these observations. In most cases, the dry delay is quite limited. It's very small, but in some cases it may be large. So it depends on the location and the time. So this is one drawback. And also, if there are clouds above your study area, your interested area, there will be no observations at all, because all the observations will be reflected by the cloud. So it will not reach the ground. So there will be no observations if there are clouds. So only valid on cloud-free conditions. This is a limitation. Another data we can use is the numerical weather models. So it also has a global coverage and very high resolution and continuous both in space and in time. We have over 40 years of numerical weather model data available currently, over 50 years actually, and insensitive to the clouds. So this is one example showing the performance of using this kind of data. The original one, the estimated correction map, and after correction, you can see the red one, the red signal, and were removed by this kind of observations. So only broad features of the troposphere are corrected because we have very low spatial resolution of this data. So we can only capture broad features, not detailed tropospheric signals. And this is another example using the high resolution weather models, 9 kilometer spatial resolution. So original one and the correction map, the estimated delay map. Then the right-hand side is a map after correction. You can clearly see it's much cleaner after correction using these observations, which works very well. Also, we can use ground-based data, comes from GPS or comes from radio sound, comes from ground sensors, which can measure directly the water vapor content in the troposphere. So in this case, it has a very high accuracy and very high temporal resolution compared to weather models, compared to MODIS. So, but it requires a very dense station distribution. In the UK, we have a nice GPS network. The spacing between each station is about 40 kilometers, which is relatively dense compared to other areas. So this is the performance of using this kind of observations. We can reach less than 1 centimeter RMS. So before correction, we have 3 to centimeters of RMS, but after correction, we can or reach less than 1 centimeter accuracy compared to GPS deformation. And the performance really depends on the network. If you have a very dense network, for this 10 kilometer spacing network, you will result in very small RMS, very high accuracy. But if you have a very sparse network, you will have a much worse performance. So the station spacing is a key factor for this kind of observations. And there are many different types of observations. Each observation has different accuracies. So if you compare weather models with GPS, you can reach about 1.5 centimeters accuracy. So there is 1.5 centimeter differences between weather models and GNSS, which means you can only reach 1 to 2 centimeter accuracy after correction. And if you compare MODIS, the satellite-based data with the measure models, you can reach about 3 millimeter accuracy in terms of water vapor, which means 1.8 centimeter tropospheric delay is similar to the GPS. So different data has different of accuracies. So you have to be careful when using this data sets. And you can also consider to integrate different data sets. For example, you can integrate GPS with MODIS, and also you can integrate GPS and weather model. So you take advantage of make use of the advantages from the two data sets. For example, GPS has high temporal resolution but low spatial resolution, but the ECNWF has high spatial resolution but low temporal resolution. So if you integrate these two observations, you can result in higher performances to do the correction. So this is an integrated model. So to conclude, there are different types of observations we can use to simulate the tropospheric effect, to correct the tropospheric error. But each dataset has their own limitations. So you have to consider these limitations when you choose these datasets. Okay, the third strategy is to do the atmospheric correction in time series. So if you have a time series of interferograms, not only one interferogram, you have tens of hundreds of interferograms, you can actually do much more computing to account for the tropospheric errors. For example, you have redundant observations, you can do a better unwrapping error detection, and you can also remove the orbital ramps in a network, and you can estimate DM errors. So all these errors can be estimated in a time series. So based on the spatial temporal filters, probably Andy will talk about this technique in next lecture. So I will only give you an impression of how the atmospheric effect looks like on Sentinel-1 observations in a time series. For example, in this case, there is some linearity of the tropospheric effect on InSAR measurement, on Sentinel-1 measurement. So for example, in this case, in point A, in the tropical regions, there is a high linearity, low linearity in point A, caused by the tropospheric effect errors. But for point C, you got a slightly larger linearity, which means the tropospheric error is linear through time, which is quite similar to an interseismic deformation. So which is difficult to distinguish between the two, which will cause big problem in interseismic study. So this is the linearity of the atmospheric effect on InSAR time series. And also it can have very large seasonality. So the tropospheric error has a seasonal component, which is quite similar to some deformation signals sometimes. for example, in tropical regions, point A, we have a large seasonality. You can clearly see that the tropospheric area has a seasonal component. And in point B, in Arabian, in this area, the seasonality is relatively smaller, which means there is not too much seasonal component in that area. So it really depends on the locations. So, but in most cases, we will have this kind of seasonal signals comes from the troposphere, which can be quite difficult to distinguish it from the real deformation. And also this is the randomness of the atmospheric error. If the atmospheric error is random, it becomes much more easier in time series analysis because we can use a low pass filter to remove all the random noises. But actually, in most cases, the atmospheric effect is not random. So the randomness is mostly very low in most areas around the Earth. So it's not random. So it becomes much harder in time series analysis. So this is the randomness. So most cases are not random for tropospheric error. And I will not talk about the details of the time series analysis, but here is a strategy to use in time series analysis. You can correct the atmospheric error on each interferogram individually. For example, in this case, you have over 1,000 interferograms. You do the atmospheric correction for each interferogram. The blue line is the original standard deviation of the interferogram, and the yellow line is the standard deviation after correction. So you can nearly all the interferograms are got reduced in terms of standard deviation. After that correction, your noise becomes more random, and the noise level becomes much smaller. So in this case, you can do a better time series analysis. So you can clearly see from this map that after correction, the noise level, the original noise level, the black lines, is very large before correction in a time series. But after correction, you got the red lines and the green, the blue lines becomes much smaller in terms of noise level. The larger the baseline, the longer the baseline, the larger the better the performance, because the noise is distance dependent. So if you are concerning about the long wavelength signals, you have to consider this kind of correction to reduce the noise level for long baseline measurements. So this is the velocity map before correction and after correction. So you can clearly see all these long wavelength signals are got removed by the correction, by the atmospheric correction. So we can clearly see some deforming signals from the velocity map after correction, only after correction. This is the correction, and also the distance dependency. So before correction, we have a very large distance dependency on the velocity map. So actually, if you ignore the tropospheric error, the deformation you estimated is highly dependent on the distance between 2 points. So it's highly distance dependent. But after correction, you got much smaller distance dependency on the velocity map, which in real world, the deformation should not have that high distance dependency in this region. All this distance dependency actually comes from the tropospheric error, not from deformation. So if you do not consider this kind of tropospheric error, you will result in this high distance dependency, which is not what we want in velocity mapping. So after correction, also we can remove the elevation dependency as well. So before correction, the velocity we estimated from the interferograms will have a high elevation dependency, which is not what we want in real deformation scenarios. But after correction, we can reduce that dependency very well. So it is more similar to the real world deformation. So the real world deformation will not have that high elevation dependency. All this dependency comes from the tropospheric error in this case. Not in all cases, but in this case, we have not that high elevation dependency in real world. So this is the time series analysis. So also to conclude, actually, you can use our product to do the atmospheric correction. So I may go too much in the details of the measures. Probably you may not understand all of them, but if you are not working on the research of the atmospheric correction, you can directly use our product to do the atmospheric correction. This is called you can look at the GECKO's website, and for each interferogram, what we are aiming for is that for a typical Sentinel-1 interferogram, we are aiming for 1 centimeter accuracy after correction in terms of displacement. And after correction, and if you do a time series analysis, if you use some filtering techniques, we can achieve millimeter level accuracy in terms of deformation or velocity, millimeter per year. So this is the website looks like. What the website looks like, and this is there. I developed some codes to use how to download, how to produce the correction map, and how to do the correction, and how to evaluate the performance of the correction. So there are some codes available on the website, and these are some examples of using GECKOs in different deformation scenarios in coseismic, landslides, volcanoes, or ground subsidence. There are a lot of different applications. So we have to conclude. We talk about different solutions to correct for the tropospheric error using empirical models and using external data sets, and do correction in a time series analysis using some kind of filtering techniques. So what we have to remember is that there are many limitations in each of these strategies. Whenever which strategy you use, you have always consider their limitations. And also we are organizing an EGU session next year in end of April. Welcome to join us in this session to talk about natural hazards and human activities, mainly using imaging geodesy techniques, including InSAR measurements. So welcome. That's all from me. Thank you.
Many thanks, Chen. That was a brilliant and actually very timely presentation, as we started a little later, right? But according to program, we should have at least 8 minutes, so we can give it, let's say, 13 minutes or something like that, which gives space for several questions that we got online. And I believe that there will be also some questions from the in-person participants, but yeah, I think you can hear us well, right? So maybe I will ask first of all here in person. Do you have something in your mind? Please put your hand up, and yeah, if not,
I can see questions online. There are some questions online. Can I start with the online questions or the audience in front?
Yeah, so actually we have at least one question from the audience here. So let's give the priority to the in-person participants here. So what was the question?
So the question is, what I understood is the atmospheric effect is also really depends on the scale that you are looking at. So when you are looking at when processing the larger image, the atmospheric effect is higher. So and it also very depends on the reference point that when you select which point to be selected as a reference point for a program for deformation analysis. So my question is that if we reduce if we kind of like create the subset and analyze and do the deformation on the subset, what can be also include as a kind of compensate with the atmospheric effect. And the second is that how to select this reference point for the formation analysis, or when we are looking also to the atmospheric effects.
So you
Yeah.
do you understand?
I heard that. Yeah, thank you. Yeah, I heard that. You are mentioning the firstly the distance dependency, the size of the interferogram, firstly, and second the reference point, right? So the size of the interferogram is really important, actually. The size means what kind of deformation you are measuring. If you are measuring localized deformation, for example, those caused by a small landslide or caused by a mining subsidence or by a small earthquakes. So all these kind of deformation are very localized, only occurs in a small areas. So if you are interested in this smaller scale deformation, so you may only have a small image. So in this case, the long wavelength effect of the tropospheric effect is not. You can ignore the long wavelength effect, actually. So this is because this kind of effect is independent with your deformation signal. So in this case, the smaller, because most of the tropospheric error comes from the long wavelength effect. The magnitude of the long wavelength effect is the largest among all other features. So in this case, a small image may have much less tropospheric errors compared to larger images. So for larger images, if you have a larger images and you want to measure long wavelength deformation signals, for example, you are studying interseismic studies or plate motions, large scale plate motions, you have to process large images. In this case, the atmospheric effect is much larger than the smaller images. So, but if you only have a large image, but you only want to study part of the deformation signals, so you only want to study a small areas in that image. So you can only, in that case, I don't think you have to I don't think you have to process that large image. You can only zoom in your stereo in small areas so that you can ensure smaller atmospheric effect. So this is about the size of the interferograms. So only precise large interferograms only if you are studying long wavelength deformation signals such as interseismic plate motions, TIA, or that kind of thing. If you are only study localized signals, I think you can only process smaller images to ensure that to minimize the tropospheric error. So, and for the reference point, actually if we do not consider the unwrapping errors, the reference point is irrelevant to the tropospheric error. So the tropospheric error is will not be affected by the reference point. So if there is no unwrapping errors, but if there is an unwrapping errors, so it will be really complicated. So the tropospheric error can affect unwrapping, phase unwrapping. If you have for example, you have a low coherence, or if your image is split by a lake or by a river, for example. So you have a lot of different regions separated by lakes, by rivers, by forests. So in this case, the existence of tropospheric error can affect seriously your unwrapping. So so in this case, the reference point becomes important, becomes relevant to the tropospheric error. So if you choose a better reference point, will result better results, will minimize the unwrapping error and minimize the tropospheric error. But if we do not consider the unwrapping error, so I think the reference point is independent with the tropospheric error. So you can use any reference point you want in terms of tropospheric effect. So that's my thinking of this problem.
Thank you, Chen. Do you have any other? Yeah, okay, there is another question.
Yeah, it is about the source of glucose data. The link that is provided has a limitation to download only 20 images for glucose per request. So is there any alternate source without any limitation or restriction?
You mean other limit? There's the 20 image limitations on the website for online users. What's your question? Do you mean are there any other limitations or?
No, is there any other data source where we can download data without any restriction or limitation?
For
Also,
online users, for individual users, we set the limitation because we don't have that high that computing power, that high computing power. If there are too many people downloading hundreds of images together, so we don't have that bandwidth, we don't have that computing power. So that's why we set the restrictions, set the limitations on the website. But if you are really interested in large area or longer time series, and it is really important to your research, you can email me. You can email me, and I can process it locally on on another server, actually, not on Geckos, and I will send you the results. So if only do it if necessary. So
thank you.
Yeah.
I may add that there is also option if you work within the InSAR data. We often have like maybe 80% of epochs that we process have already Geckos corrections, as we download them like directly to the InSAR.
Because the Gecko server are now processing all the corrections for leaks interferograms, and for another satellite mission in China. So we have two large users which will need thousands of interferograms all the time continuously. So we are processing interferogram correction maps for them, for COMET and another user in China. So it's really the computing power is really limited. It's really expensive, actually. So that's why we set the restrictions.
So we can have 5 more minutes. So if there are some more questions, please go on, as we have a couple of online questions as well, but these can be also answered a little later. Nobody? So, Chen, would you like to answer several of those online questions live, and the rest by writing them, as we will have a break in 5 minutes? I try to find some, well, they are all topical. So what do you think? Can we start with the first one? Just the first one, like, how can the atmospheric artifacts in InSAR be identified and differentiated from deformation signals in the presence of strong topographic variations?
Yeah. That's a good question. Actually, if we know the deformation is not correlated, is not dependent on elevation, which is in most cases is true, unless around volcanoes. So in most cases, the deformation is uncorrelated, independent with the elevation. In that case, we can use a very simple linear equation. We can assume that all tropospheric errors are correlated with the elevation. So we can use a very simple equation to simulate to estimate the elevation correlated dependent tropospheric errors. So after estimate that tropospheric error, we can remove it from the interferogram. So actually, it means that you remove all the signals that are correlated with the elevation. So the remaining signals are the actual deformation. So that's how can we differentiate it? How can we distinguish the deformation signals from the tropospheric error in strong topographic variation regions? So that's one technique. But if you are studying volcanic deformation signals, I think it's probably not a good option because the deformation around the volcano can have large relationships with the elevation as well. So if you use that simple equation, you may risk of removing all the signals, including tropospheric error and the deformation. You remove all of them or part of them. So it's dangerous in that case. Okay.
Thank you, Chen. So we still have 2 minutes, not more than 2 minutes, which I think we can have just one question left. So nobody from in-person participants. So let me select one other that I found topically interesting. So can you mention about the effects one will encounter when consider a study area along coastal regions, and how can this be resolved?
Sorry, I didn't find the question.
Oh, that's a little bit at the end, because you know the most of the other questions are rather easy to grasp, but that one was considering study area along coastal regions.
Oh, coast areas.
Yeah, yeah. So what do you think? Is it rather ocean tide loading issues or
Yeah. Things becomes much more complicated in coastal areas. That's for sure. Yeah. Not only for atmospheric effects, but also the ocean tide loading effect. So in coastal areas, the weather, the environment of the troposphere changes very rapidly because of the storms or the cyclones or the rainfalls or the convection between oceanic troposphere and the coastal troposphere. So it becomes very complicated in terms of the tropospheric environment. So in this complicated troposphere environment, we will have much larger, much serious tropospheric errors. And more complicated. Some of the features, some of the errors we still don't understand very well. So it's very hard to predict, very hard to observe. We need very high resolution in that case, and very hard to model. So in that case, we have much, we may probably have worse performance no matter which measures you are using. So we need to pay much more attention when processing coastal areas. But not all coastal areas have this kind of problem. For example, I guess in the west coast of UK, west coast of England, have much smaller ocean tide loading effects compared to the east coast. So not all coastal areas have this kind of problem. Only some, for example, the west coast of England east coast of China and the west coast of the USA. So these kind of areas have larger ocean tidal loading effects, probably larger tropospheric effects, but not all coast areas have this kind of problem, depending on the environment, depending on the troposphere. So there is a map in my presentation to show the magnitude of the tropospheric effect, and there are also a paper shows the ocean tidal loading effects globally. So not all coastal areas have this problem. You can clearly see the magnitude. So yes.
Okay, so I'm afraid we kind of run out of time. Even I remember there were some questions, like for example, why there is the magnitude much higher in India. If you can just comment very, very briefly, and then we will end up this session.
Yeah. The simple answer is that the weather in India is more wet than other areas. So it's more wet, there will be more water vapor, and the temperature is also very high in India. So the temperature is high, the water vapor content is high. So the tropospheric effect is much higher in India. Also because of the climate, the climate conditions in India changes very rapidly from time to time, each in 1 year. So it changes very rapidly. So the spatial temporal changes of the water vapor, of the temperature, can be very high. So the errors from the troposphere is extremely high in India. So that's why.
Cool. I think it's very, very, very interesting and enlightening talk. So thank you very much, Chen. Thank you very much.
Yep.
And yeah, hope to see you maybe at
Yeah.
CIW or somewhere else.
Yeah.
Okay.
So enjoy.